Okay, it's a lesson on 8.5, multiplying and dividing radicals. So just for some background information and skills that will be applied in this lesson, let's consider what happens when we multiply root 2 by itself. Well, let's also remember that when we have this property called that we've already seen, called the square root of a product property, and that says if I have the square root of AB, that equals the square root of A times the square root of B, and we've used that a lot. That property works both ways, so if I had the square root of A times the square root of B, I could make that, if I wanted to, AB. So with that line of thinking in play, if I have the same radical, like the square root of 2 times the square root of 2, I can make that, if this was the square root of A times the square root of A, that would be the square root of A squared. So I have the square root of 2 squared, which is 4. The square root of 4 is 2. So if I have a radical expression times itself, that has to equal the radicand. So notice 2 is the radicand. So the square root of 2 times the square root of 2 is equal to 2. So a few more examples. The square root of 3 times the square root of 3. If I apply this property, that equals the square root of 3 squared, which is 9, square root of 9, which is 3. Square root of 7 times square root of 7 is 7. So that would make the square root of x the square root of x times the square root of x equal to x. And so now let's think about what would happen if I multiply cube roots together. So the cube root of 2 times the cube root of 4 would make the cube root of 2 times 4, which would equal the cube root of 8, and that's a perfect cube, so that equals 2. Similarly, if I have the cube root of 4 times the cube root of 16, that would equal the cube root of 4 times 16, which equals the cube root of, instead of multiplying that out, it's 64. I could just say, well, that's 4 times 4 squared, which is equal to the cube root of 4 cubed, which is equal to 4. Here I have the cube root of 3 times the cube root of 9. That would be the cube root of 3 times 9, or the cube root of 3 times 3 squared, or the cube root of 3 cubed equals 3. So you don't have to show all your work like that, but that's just to explain, a lot of the little ways that the multiplying is going to work when you're working with radicals. So in this first example, I have the square root of 2 times the quantity, the square root of 2 plus 1, so I'm going to have to distribute here. And so when I multiply the square root of 2 times the square root of 2, that's just going to equal to 2, and then plus the square root of 2 times 1, which is the square root of 2. So that's all I have to do there. And the next one over here, I have the square root of y times the quantity, the square root of y plus 2. So I'm going to multiply the square root of y times y and the square root of y, and then add to that the square root of y times 2. So the way I'll write my answer there, square root of y times y is just y, and then square root of y times 2, I'll call that 2 root y, and those are non-like terms. So that's my final answer. Next one, I have the square root of 3n times the square root of 15n. So that way, and then times the quantity, the square root of 15n plus the square root of 6n. Those aren't like terms. I can't put those together before I multiply. So I'm going to say the square root of 3n times the square root of 15n is the square root of 45n squared. And then the square root of 3n times the square root of 6n is the square root of 18n squared. Now I have to break these radicals down. So this sort of things that become yesterday's lesson. So this is the square root of 9n squared times 5 plus the square root of 9n squared times 2. So I'll have 3n root 5 plus 3n root 2. Since the radicals aren't the same, that's as far as I go. It doesn't matter that I have like terms before I'm multiplying by the radicals. It doesn't matter that those three n's are the same in like terms because the radical expression part of it is different. So the next one, I've got the cube root of 7 times the cube root of 49 times the quantity of the cube root of 49 minus 2. So I'm going to take the cube root of, so that's going to be, remember the 49 is 7 squared, so I'm going to have 7 times 7 squared there, that's a cube root, and then minus 2 times the cube root of 7, and then this ends up being the cube root of 7 cubed minus 2 cube root 7. So that's just a 7 minus 2 cube root 7, and that's my final answer there. Now, next kind of concept we have to add is when we're dealing with radicals and multiplying is multiplying what we call conjugate binomials, and we've done this when we were working on operations with polynomials. So remember, conjugate binomials are binomials, two terms, that's a binomial. Only difference is the sign between them. So remember that when we had that situation, if you were to apply FOIL to this, which is, I want you to remember this more than I want you to apply FOIL, I want you to remember what the pattern is. If I did first and then outer and then inner and then last, notice that the O and the I of FOIL generate opposites, so you end up with 0. So you just end up, so when you multiply conjugates, you just end up with the F and the L of FOIL with a subtraction sign between them. So that gets x squared minus 36. So if I were to do this one over here, so you really don't have to do FOIL because you know the O and the I of FOIL, when you're multiplying conjugates, it's going to get a 0 for the sum of the O and the I. So therefore, you just know that it's the firsts multiplied together minus the last, which is 5 times 5, 25. So that we're going to use that concept a lot with multiplying radical binomials. So you have that right here, the square root of 2 plus 1 times the quantity of the square root of 2 minus 1. So those are conjugates, so we just need to multiply the square root of 2 and then say minus 1 times 1. So the square root of 2 times the square root of 2 is 2, and then the 1 times negative, and then it's minus 1 times 1, so all of that just equals 1 right there. And this next one, square root of 6 plus 7, that quantity is plus root 7 times the quantity root 6x minus 7. So remember, we're going to multiply the first and the last with a subtraction sign between them. So the square root of 6x times the square root of 6x is just itself, and then minus the square root of 7 times the square root of 7, which is 7, and that's all I can do there. Move this up now. Whoops. So in this last example, I have the quantity, the cube root of 4d squared plus 5 times the quantity of the cube root of 2d minus 3. So when I multiply the first together, I get the cube root of, Well, 4 times 2 is 8. I could make that 2 cubed if I wanted to, and then d cubed, and so that's what all that equals. I'll take the cube root in a second, and then I have minus, or actually on this one, these aren't conjugates, so let's back up for a second here. So this one, these are not conjugates, so I am going to use full-scale FOIL on this one. So then I'm going to have to multiply the outers, which is minus 3 times the cube root of 4d squared, and then plus the inner, which is the cube root, so that's 5 times the cube root of 2d, and then finally I'll have last, which is 5 times negative 3, and I'll have minus 15. Well, this first term here is a perfect cube. I've got 2d, and then there's nothing I can do with these, so I'm just going to write this just like so. I have non-like terms everywhere, so I have to leave it just like so. Okay, we're going to next talk about what's called rationalizing denominators, and I would like you to recall that the third criterion for a simplified radical is there cannot be a radical in the denominator. Thus, you can't leave an answer like 1 over root 2 because of this radical in the denominator. So what can we do? Well, we can do what's called rationalize the denominator, which means we can make the denominator rational, and that's what we're trying to do. And there's a technique we'll use to do that. And make it rational, there'd no longer be a square root in the denominator, or a cube root, whatever the case may be. All right. So if I'm dealing with 1 over root 2, the way I would get rid of that radical in the denominator is actually multiply by root 2 over root 2, which when you multiply something over itself, that equals 1, so I'm not really changing the value of it. And so this ends up being root 2 over 2. Now that doesn't look to be more, particularly, have a simpler look, but we all have to agree that no, there's no radical in the denominator, so this exactly equals that, but it's considered to be simplified. Okay, so let's see how this helps us. If I have 3 over the square root of 11, I'm going to make that, I'll just rewrite it, and then I'm going to multiply by the square root of 11 over the square root of 11, and I'll leave my final answer here, 3 root 11 over 11, because that's what the square root of 11 times the square root of 11, so now that's considered simplified. In this next one I have 3 over, and I'm going to make that root 9 times 2, do some simplifying first before I rationalize the denominator, and that'll be 3 over 3 root 2, and that, so I can cancel those 3's, so right now what I have is 1 over root 2. I'll rationalize the denominator just like I did on the previous page by multiplying square root of 2 over 2, and I get root 2 over 2, and that's my final answer on that one. In this next one I have the square root of 3xy times the square root of 4x, so I'm going to leave the numerator alone for a second. No perfect square factors there. I do have a perfect square factor in the denominator, so I'm going to take that out. Then I'm going to multiply by the square root of x times the square root of x, and that will be That's going to get me is the square root of 3x squared y over 2x. I can pull that perfect square factor of x squared out of the numerator, and I've got 3y over 2x. I can actually cancel that x out, and that'll leave me with a final answer of cube root of 3y, no, sorry, the square root of 3y. Let me clean that up a little bit. Over 2. So we have my final answer on that one. Okay, last example on this page. I have the cube root of negative 16 ABC over a squared b cubed c cubed. I think I'm going to go ahead and just distribute here, and while I'm doing that, identify perfect cube factors. Negative 8 would be a perfect cube factor times ABC, and then in the denominator I have these two cube terms, so those will be the perfect cube part of that. And remaining I have an a squared. So in the numerator I'll take the square root of negative 8 and get negative 2. I mean the cube root of negative 8, negative 2. And then I'll have root ABC. Then I'll have the cube root of b cubed and c cubed, which is bc times root a squared. In order to rationalize the denominator here, I've got to get another a in there. I don't want to multiply by itself. But since it's the cube root, let me get my cube roots back in there. I need to multiply this by just root a, because I want to get this right here up to an a cubed. And so that's going to get me negative 2 times the cube root of a squared bc over these together, this a cube root of a. And by the way, I got to make sure I keep including my 3's in here. And so that's going to get me that a squared and the cube root of a squared and the cube root of a are going to just make an a, so this just becomes a, b, c in the denominator. And I think at this point I can consider myself done. There's nothing else I can cancel. All right, notes. What happens when there is a binomial radical expression in the denominator? So I've got a binomial down here. And so what I'm going to do to rationalize this denominator, I can't just multiply by the square root of 5, because that'll then also have to get attached to the square root of 2, and I'll just be like a rat in a maze. So what I've got to do here is, in order to have the radicals disappear, I've got to multiply by the conjugate of root 5 minus 2. And remember, a conjugate is the same binomial except for the sign between them. And that will force the radical to drop out of the denominator. Otherwise, if I use anything else, I'm still going to have a radical in the denominator. So remember, we multiply conjugates. There's going to be no middle term for the O and the I of FOIL generated by the O and the I of FOIL, because they'll be opposites. So we're just going to have the first and the last multiply together with a subtraction sign between them. So in the denominator here, I would have just 5 minus 4, so that's just a 1. And the numerator, I have 3 root 5 plus 3 times 2. So that will leave me with 3 root 5 plus 6 over 1. So that's our final answer. We're going to do the same thing in this next example. I've got root 2x minus 5 over root 2x minus 3. I'm going to multiply by the conjugate of the binomial in the denominator. Write that x a little bit better. So 2x plus 3, root 2x plus 3, and that will get me in the numerator. I've got to multiply these binomials using FOIL. In the denominator, things are going to clean up pretty quickly. So in the denominator, I'll have, let me go ahead and throw parentheses around there. And so that will get me, just if I do the f and the L of FOIL, because there'll be no middle term, I'll get 2x minus 9. In the numerator, when I do FOIL, I've got root 2x, I've got root 2x times root 2x, and that's just a 2x. And then I do have to do full scale FOIL on this because these are not conjugates. I've got root 2x times 3, so that's 3 root 2x. And then I've got negative 5 times root 2x, so that's minus 5 root 2x, and then I've got negative 5 times 3, so that'll be minus 15. So I do have some like terms together right here, so that's going to be, so I'm going to end up with 2x minus 2 root 2x minus 15 over 2x minus 9. Do not try to cancel because you don't have things in factor form in the numerator, and there's just nothing else that can cancel out here. So with that said, I believe this is the end of the lesson. So good luck with this assignment.